Okay, so let's look at some examples of how we can use the malloc and free functions in order to dynamically allocate memory as required for our purposes. Now this function that I have out here is a fairly simple function. What it does is it basically declares p as a pointer to an integer, right, int star p. Now it's sort of interesting to think, okay, what happens when I just declare something as int star p? What is the value in p, right? Now we know that if I just declare a variable int a and then ask, okay, what's the value in a, that's actually undefined. C does not guarantee that that value is actually going to have, that variable is going to have a specific value. In the same way, a pointer is not guaranteed to be set to 0 or to any other known value, right? If you are lucky, it might turn out that yes, it turns out to be 0. So in fact, maybe we could just take a look at that, right? Does that in fact happen? If I just try printing out the pointer, right, I can see that it just prints out some number out here, right. Now how did that happen? What does this number correspond to? I have no idea. I have not requested that number. It's not clear where it came from or what it corresponds to. Does it correspond to an actual physical memory location or not? We don't know, right. So the bottom line is, when you just declare a pointer and you have not initialized it, you have to be very careful with it, because it's quite possible that it actually points to some location in memory, right. And you are probably better off if p actually explicitly had the value 0, right, because if it did have the value 0, then it's quite clear that you should not be messing around with it. When you try dereferencing p of something, it will complain and immediately stop your program right then and there. Even worse is if p actually points to a valid location in memory and purely by accident your program continues to run. You are not even going to find out that there was a bug over there until one day it runs with some unknown initialized value, which actually corresponds to some other data that you have and causes the program to crash. Bottom line, make sure that you initialize variables anytime that you declare them, right. Do not use uninitialized variables. There will typically be, there will typically be some kind of editor help, right. So if you are using the Visual Studio Code, for example, it will usually have some kind of lint capabilities. Linters are programs that basically look at your code and warn you about potential problems with them, right. And there could be linting capabilities that tell you that, look, you are trying to use a variable before initializing it, right. You can run into problems. In this case, there was nothing. It did not give you a warning. The warning that it is giving over here is about something else. It's basically saying that it's the wrong type to be printed out over here, but that's not the actual problem that we need to deal with. So bottom line, don't do that, right. But what we can do instead is, I can malloc memory, okay. And what I am doing over here is I am calling the function malloc. The argument to that function is 20 into size of int, okay. So let's unpack that. Size of int is something that the compiler knows. It knows that an int in this case is 4 bytes, and therefore 20 into 4 is going to give you the number 80, and that is what I am passing into malloc, which means that I am actually requesting it for a chunk of memory of size 80 bytes, okay. What does the combination runtime plus operating system, whatever it is that actually executes that malloc function, right, what it does is it goes in the memory allocated for this program, identifies a suitable chunk of memory of size 80 bytes, finds the pointer corresponding to the beginning of that memory and returns that to me. The problem is that pointer, malloc, what it does is it returns what's called a void pointer. It's still a pointer, it's 8 bytes in size, it points to a memory location, but the compiler is going to complain anyway, because it says, hey, malloc just returned a void pointer. What kind of pointer do you actually want, right? The answer is, of course, that we want an int pointer. Why is that relevant? Because when we start doing pointer arithmetic, that is, we try to access a particular location in memory either using the p of notation or the p plus offset notation, the compiler needs to know how many steps forward to take, and to do that it needs to know what kind of pointer p is supposed to be. Now in this case, I have already declared p to be an int pointer. So you could argue that the compiler is being needlessly complaining over here. After all, it should know that I want an int pointer, and why not just take care of that by itself? Yes, arguable, right? This is one of those choices that the compiler made, where it basically says that if I do not do an explicit typecast, it will complain. Okay. So fine, what I have done is I have taken p, I have taken malloc, I have cast the output of malloc as an int star and assigned it to p. And now what I can do is, if I go ahead and print that out, right, it should run, and you will notice that it has printed some number out here, right, this 2365096, okay. What does that number correspond to? We do not know. All that we can say at this point is, it is some address in the virtual memory corresponding to this program where you are allowed to allocate memory, right. So the program took care of allocating memory for you, and it returned a value, and incidentally it returned a non-zero value, right. Usually after running a command like this, p is equal to int star, the first thing that you should actually check is p equal to null or not, right, because if p is equal to null, it means that the malloc actually failed. In this case, since I am printing it out, I can see that p was not null, right. So the malloc succeeded, which is why I can safely say that this actually corresponds to an address somewhere in the memory of the system. Okay. Now what that means is, I can go ahead and start using it like an array, p of 0, right. I can also do something like p of 5 is equal to 50, right. All of this works, and then I could even go ahead and print this stuff out, right. So what happens out here is, I am asking it to, let us say, print the first 10 values, right, and you will see that what it is actually doing is, I am asking it to print p of I. What does it do? P was declared as an int star. So p of I, right, this is exactly equivalent to star of p plus I, right, where I is treated as an offset of an integer type, because after all p is of int star type, which means that every plus I that I do is actually adding 4 to the address, right. So let us see how exactly that works. When we run this, we can find that sure enough, at this location I have 20, at this location I have 0, 0, 0, 0 and then 50, right. As far as I can tell, it is purely a coincidence that all of these values turn out to be zeros. There is nothing in the language guaranteeing that, right, and in fact there is no way in general that you can guarantee that some value sitting in the heap memory is going to be initialized to 0. Remember, I used only malloc and not calloc, okay. Now you might wonder, okay, what happens, can I go up to 20? Yes, I should be able to do that, right, and I can run this, and yeah, sure enough it is able to print all the values out, and interestingly enough it actually all those values seem to be 0, right. What happens if I give 30 out here? Okay. Well, let us try it, run it and see, and sure enough it goes ahead and prints, it does not complain, right. What has happened over here is that after the 20 we start seeing some garbage values, right, and that is not because of the malloc. Remember, malloc does not guarantee initialization. So it turns out that these values were 0, but the values after that actually turn out to be garbage. That is not because I malloced only 20 values, right. It could be purely by accident that it ended up having that number there. Okay, so now we have seen how we can allocate memory, we can start assigning values to the various places that are there in the memory, and we can print them out. We also saw that if the I, the offset that we have over here, is greater than what we allocated, the compiler does not complain, the runtime does not complain. If you are lucky, you still end up within the memory that is allocated for your program, right, and you do not run into any errors, right. but there are no guarantees about that. It's entirely possible that if you are not careful, this offset could end up outside the range that's permitted for your program and potentially crash it. Okay, so far so good. Now we have this function called free. What does free do? It tells the runtime and the operating system, I'm done with this memory, you can take it back, right? And as such, if I was to run this, you would see absolutely no difference in behavior. I still see exactly the same output as I had before, right? The address is some number out here, there are all these values that get printed out, and that address alone changes every time I run it. But apart from that, the values by themselves, it seems to behave properly as expected. But after the free, what would happen if I now went ahead and looked at the value of the address, for example, right? If I just asked it again, hey, I have just freed up this pointer, now what's the address that I have, right? And just to make things clearer, I am only going to print out the first 5 values, right? And let's see what happens when we do that. So what we have over here is I am going to allocate 20 integers, assign some values to them, print out the first 5 of those integers, free the pointer, and then once again ask what is the value of the address and what are the values that I have out here, right? Let's see what happens when I do this. Now what you can see is, the first time around the address was 3277 something something, right? And it had this value 20 because after all I placed 20 in P of 0. The other values turned out to be zeros over here, right? But after that, after I call free, the next thing that happens is I have also assigned P of 1 is equal to 30. It did not complain, right? It did not tell me that you have already freed the pointer, why are you trying to assign a value to it? It went ahead and did something. What did it do? We can see that in the offset 1 from this address, it has actually put the number 30. But interestingly enough, the rest of the numbers now have some strange values in them, right? Now you might wonder, why did these numbers already get messed up so quickly? And short answer is, we don't have a easy way of knowing that. Most likely what has happened is that one of these other functions, either free or printf or something else, allocated some memory on the heap, and by doing so it actually caused some data to go and sit in those numbers in the heap, right? What exactly happened, we can't say for sure, right? But it looks as though what has ended up happening is that the data just got, some numbers got written into the heap, right? But when I tried accessing P of 1 is equal to 30, it did not complain, even though that memory has been freed. This is something you have to be very careful about. Basically what it's saying is that you have finished freeing a pointer, but you are still continuing to use it as though it belongs to you. You are effectively like an unreserved ticket traveling in a reserved compartment. You don't know at what point this data will get overwritten, and as you can see, yes, it does get overwritten because any other function call might end up writing some other data into the memory that you have there. Okay. Now finally, what happens if I call free once more out here, right? Once again, this is not technically an error, right? But it does sort of warn you, saying that you have done a double free. Double frees are once again potentially very problematic, right? The reason why the runtime is complaining. So this is an error which is coming, or rather it's a complaint coming from the runtime of the program, not from the compiler. The compiler did not say anything about it, because only after running everything does it actually say that double free was detected, right? Double frees can be dangerous. Effectively what you are doing is you are trying to free a pointer that does not belong to you, that you have not allocated, right? And as a result you can potentially end up freeing up memory which somebody else thought was actually reserved, and after that it then goes and reuses the memory for something else while you think that it can be used in a different way, right? Once again potentially can lead to security issues, can lead to programs crashing and so on, right? Using pointers in general in C is something you have to do with care. You have to be a little careful about how exactly you are going to make use of it, right? But as long as you sort of keep it relatively straightforward, you allocate memory, you use it, you free it when you are done, things should work out perfectly fine. The tricky parts are when you need to sort of handle things down at the system level, right? You need to actually know how to allocate, deallocate in such a way that the memory utilization is kept optimal. Unless you are actually going into an operating system or something, it is very rare that you would need to do something of that sort. These are things to be aware of, but you should not really be doing any of these tricky operations with malloc and free, apart from just allocating and freeing, of course, unless you really understand what pointers are all about. So now let's look at some code out here which helps us to understand a little better of where exactly the different memory elements are allocated, right. So I am declaring two variables out here. One of them is just an int a of 5. This is an array of integers, and as we know, arrays and pointers can be thought of as almost equivalent, right. You can always sort of dereference a pointer to make it look like an array indexing operation, and you can also take the address corresponding to an array and treat it as a pointer, right. B on the other hand is explicitly just declared as a pointer to an integer. Okay. Now with that, what I am going to do is first print out these values out here, right. The first value that I am going to print is a, and remember that a by itself is an array. A of 0 is an int, but a by itself is an array, meaning that it is a pointer. In other words, when I ask it to print a, this is sort of equivalent to saying print ampersand a. In the case of an array, a and ampersand a are basically the same. They both are the pointer corresponding to the start of the array. Now b on the other hand is of type int star. B is a pointer, right. So if I ask for what is the content of b, I am asking for what does b point to, right. And finally, what about ampersand b? B is a variable that has been declared as part of this function, which means that in order to hold b, space has been set aside on the stack frame corresponding to this function. So there is a space for holding a pointer in the stack frame of this function. That space itself has an address. That is what ampersand b corresponds to, right. In most cases, it is very unlikely that you would need to find the address of a pointer variable, but if at all at any point you do want to find the address of a variable, you can do it. B is just a variable like any other variable, okay. So what happens when we print this out? We find that a has some value out here, right. So 0x294f, it does not matter, it is some long hexadecimal number. B has the value 0, right. Interestingly enough, it looks as though when I declared int star b, it actually got initialized to 0, which is good news, right. The point is I have not initialized it. It could have been anything. In this case, it turns out to have been 0, that is all. But now look at ampersand b, and what I find is that this is some DA48, right. Let me change this from, instead of having hexadecimal, I am going to print them out as unsigned values, right. And when I run this, so when I run this printf, having changed the format specifiers to LU, basically long unsigned, what I find is that A, which is the address of the array of 5 elements, has some value ending with these numbers 480. The content of B is 0, which basically means it is pointing to 0, but the address of B is this number 472, right. If you think about it, basically what this is telling you is B is the address of B, in other words, is some memory location that can hold an 8-byte value, a 64-bit value, which is a pointer. So 8 bytes are stored over here starting at location 472, and A then has another, well, some number of bytes starting at location 480, right. Why did that happen? Because of course we are going from high memory to low memory, right. So the address of A ends up being higher than the address of B. That is just once again an artifact of how memory allocation happens in a little endian system, right? Nothing guaranteed by the language, it just so happens because of the particular compiler and architecture that we are using. But what you can see is both of these numbers start with this 140 etc. and end up very close to each other. Okay. Now let's go ahead and ask for B to get some value allocated to it, right? I am just allocating around 20 bytes over here. This is 20 bytes, not 20 integers, right? And what I am going to do is ask the system to print out the same values once again, but immediately after doing the allocation. What I expect to see is that A and ampersand B should remain unchanged, but B the second time around should have a different value, right? So let me just change this to also to long unsigned, just so that we can sort of compare the different addresses that we have here, right? And now if I run this, what I find is the first time around we can see that A has some address 9456, B has some other address 9448, they are 8 bytes apart, B is initialized to the value 0. The second time around when I print the second printf on line 32, the address of A remains unchanged. I am still inside the same function, so the address of A should not have changed. The address of B also has remained unchanged, but the value of B is now a totally different number. More importantly, if you look at the value of this number, you will see that this number is very different from these numbers that we have out here, right? The address of A and the address of B are some multi-digit, more than 10-digit numbers, whereas the address of B is a small, only 8-digit number. It is a much smaller number, right? Why is that? What it means is it's in a totally different area of memory than where A and B by themselves are stored. So B points to a location in memory that is very different from where A and B, the variables, are stored. Okay. That, in other words, is telling you roughly where the stack is and where the heap is, right? So the address of A and the address of B are somewhere in the stack corresponding to this particular function call, whereas the address that got assigned as a value in B, right, as a result of malloc, is in a totally different location in memory, right, and that is in the heap part of the program. Okay, so now with that in mind, let's just declare a few more variables, right, and take a look at some of their addresses just to sort of understand this distinction between the stack and the heap a bit better. C, D, E, all of these are now variables, right, that have been declared inside this function, which means that all of them, right, when I print out ampersand C, ampersand D and ampersand E, I should find that their addresses correspond to different locations inside the stack area of this program. Okay. I will just comment out these other two lines out here to make things a bit more clear. And then what we find is I have also declared two more variables. One of them is a char star s, right, and I am initializing it to a value, right, which is something that is, it's a constant string. Okay. Where does this go? Will this constant string get allocated in the stack corresponding to this function? Will it get allocated in the heap area, or will it get allocated somewhere else altogether? Right, that is something that we need to find out. And similarly, what if I declare another short star ss and do a malloc immediately corresponding to that? Where does this go? As a guess, what I would expect is that the address corresponding to C, D and E should all be in the stack. The result of this malloc, so in other words ss, should be in the heap, and s, well, I don't know, let us find out, right. And when we run this, what we find is, okay, sure enough, A has got some address which is 9460 something 300. I am printing out B here, not ampersand B. So B is basically what got assigned on line 31 out here, that is to say it is an address in the heap of the system. So this thing starting with EDE is somewhere in the heap of the system. You can see that this number is very different from all these 9460, 9460 numbers that we are seeing. C, D and E, right, as expected all three of these end up in the stack. They have addresses very similar to what A has, right. So, it is 2FE, 2FD, 2F8, right. And if you look at those numbers, you will find that those are all related. 300 hex, a few bytes below that is 2FE, right, basically 2 bytes below that is 2FE, 1 byte below that is 2FD, and then we have something else which is the int E, which is 4 bytes but aligned to a multiple of 4 below that. So, A, C, D and E all end up in the stack, in fact in more or less consecutive locations. If I look carefully, I will find that B also potentially belongs somewhere in the stack, that is the address of B, but what B points to is to a completely different area of memory, that is in the heap. Okay. Now what about SS, which I called with malloc? That has an address very similar to what happened with B, right. So in other words, both the mallocs seem to have ended up very close to each other. As expected, both end up somewhere in the heap. Okay. S on the other hand, this char star that I have is a totally different address. It does not look anything similar to the addresses of A, C, D, E, which are in the stack, nor does it look similar to the address of B or SS, right, or the address pointed to by B or SS, which have been allocated on the heap. What has ended up with S is that it is now pointing to some location in a totally different area of memory. As I mentioned earlier, this area corresponds to where the constant data of the program is stored. So pretty much only the strings used by the program are going to be found in this part of memory. Okay. So the point of all of this was to show how you can sort of identify where in a given part of the memory of the system the different chunks of data that you are using will go and settle, right, and it can be useful to sort of understand the stack versus the heap and how they get allocated based on that.